Hello! In this class we're going to extend our knowledge on functions. We're going to look at how we can represent them, and we know that representing in maths means to draw graphically. So how can we draw or represent as a diagram a function? And that's known as a mapping diagram. We're going to look at how functions are named and how they can also appear in an input-output table. So first we're going to recap what we learned in the last class. So we remember that a function is a rule. It might be a calculation, such as to add 4, or times by 3 and then take away 2. And that rule maps an input, something that we start off with, to a unique output. It changes it to its answer. Notice that we use the word maps. We refer to maps when we alter something. It appears in one particular format and then changes to another. And that will help us when we start to look at mapping diagrams later on in this class. In a function, the number that you put in, so we call that the input, is changed into another number, the output, according to that certain relationship, that rule, the calculation that we are undergoing as part of that function. We learnt that when thinking about functions, it can be easier to think about them as a type of machine, where we've got a material that goes in, an input, and some operation is performed on it, and out comes a result. So for example, we can put our 2, 3 in our inputs in, and we might get the numbers 4 and 6. In that case, the function had the rule of doubling. So each of our inputs was doubled, multiplied by 2 to get our outputs. Let's remind ourselves of another function. We could start off with the input 2, we get 4, and 3 gets 9 this time. So the rule in this case is not a doubling, but instead it's being multiplied by itself. The input has been squared. So the rule is the input is squared. So let's start looking at how we can represent our functions. One method of showing a function is to draw a mapping diagram. In a mapping diagram, each input, what we start off with, is mapped to its output. For example, we're going to look at the mapping diagram for a function which we've named with the letter G. Now, the most common way of naming our functions is actually the letter F, which is quite useful, F for functions. But as we have learned with lots of other topics in maths, if we have more than one of the same thing in a particular question or a study, we want to make sure that we can distinguish between each. For example, when we were looking at lines, we might have a line L, but then another one might be M or N or any lowercase letter. Well, it's the same here for functions. We might have a function f, and then the second common function label is g, and then what do you think might be the next most common? H, starting with F and going through the alphabet. But actually, you can name it anything you like, but they're the ones that would come up more frequently in an exam, F, G, and H. And for this particular example, we've been given the name of this function as the letter G. Now we have looked at representing maths for lots of topics. When we learnt about sets, we learnt about something called a Venn diagram, where we used a circle, and inside the circle we represented any elements of that set. And a set is a group of objects that all have something in common. Well, if you think about it, our inputs, they're all sharing something in common. They're about to start off as being put into this function. So they can be treated as a set themselves. And therefore, it becomes more easy to understand why we might use a circle or an oval, a bit like we did with a Venn diagram, to represent that set. So here we have it. We've got our oval, and this is our inputs. So all of the numbers that you're going to put into that function, the numbers that you start off with, our inputs, are placed inside that circle. And just like we did when we learned about sets, we must have a little dot to represent exactly where that element, or that input in this case, belongs. So the dot is clearly identifying the fact that 0 is an input because it's inside this oval. Now likewise, we will have another set for our outputs. And you can imagine then that that would make sense for it to appear alongside it. So here are our outputs, the elements 13, 4 and 1. Now what you'll notice then is that we have this arrow which helps us to show the path or the mapping or the connection between which input and which output. So if you look at this top arrow, we see that the input 4 is mapped, so it's transformed, it becomes the output 13 after it has gone through this function. So once the rule of that function has been applied, the number 4 results in the output 13, and 1 with 4 and 0 with 1. So just like with all maths, we would make sure that we would draw with a pencil, a sharp pencil, that we would try and make things as neat as possible. Now you'll notice one more thing on our diagram, and that's that we've put the name of the function just above these arrows. And this would be a typical example of what a mapping diagram looks like, of how we can draw a function. Can you guess what the rule is of our function g? Well, it's to multiply by 3 and then add 1. Let's check it out. 4 multiplied by 3 is 12. Add 1 gives 13. 1 times 3 is 3, add 1 is 4. 0 times 3 is 0. Add 1, we get the output 1. The rule, multiply by 3 and add 1. In the last class, you can recall that we learnt that we're often asked to identify whether something is a function or not, and that we learnt there are a few important properties, that requirements, in order for a function to actually exist. So when a function is shown using a mapping diagram, it's sometimes easier for us to check then whether it actually is a function. Let's remember some of the things that we learnt in the last class. We learnt that no input will map, transform, or result in 2 or more outputs. If you start off with one number and you perform the same calculation, you're only going to get one answer. So if you look at our first mapping diagram, we've got one input that is being mapped to 2 different answers. One to many. That's not right. So therefore, this function, which has been given the name f, it's not a function. And our reason why, if we're asked to explain, is that no input will map onto 2 or more outputs, or simply that every input must have one unique output. output. We also learned that a function does, though, allow the opposite, the reverse. There can be two numbers that we start with that will undergo the rule and map to the same answer, the same output, which is this middle diagram here. We looked at how both -2 and +2, so that's two different numbers, two different inputs, when they are squared, multiplied by themselves, they both give the answer 4. They both have the same output. So we end up with one answer to two inputs. So if we go from left to right, the start, putting something in and ending out with what comes out, we can have many turning to 1. So this is an example of many to 1, and we know that that is okay. So therefore, f is a function in this case. And then lastly, we learned that a function has to have an output for every input. And if we look at this last diagram, you'll see that there is an input here at the bottom that does not map to anything in our output set. Therefore, this is not a function, and our reason is the input has no output. A function can also be written as a set of couples or ordered pairs, and we looked at this in the last video. In each couple, as we call them, and it's easy to understand why it's called a couple or an ordered pair, because couple and pairs means two of, and having them ordered is quite important. We start off with the first of the two numbers being the input, what comes first, and the second is what comes out, the output. In each couple, the first element, the input, is then related to the second element, the output, and we know that they're related as a result of the rule of that function. So on this mapping diagram for function f, you can see that the input a has the output 1. And we know that each couple or ordered pair is written as, we have a bracket, the input, a comma, that input's output, and a closed bracket. So therefore, here we have the entire set, and we know that sets are appearing in a pair of curly brackets. So we have here the name of our function, and we know that that is equal to the set of our curly brackets. And then we have all of our couples or ordered pairs together inside that curly bracket and separated with a comma. So we can see that the input A has the output 1, the input B has the output 4, input C has the output 3, and D maps to 5. When a function is written as a set of couples, there will be no two couples that have the same input, because we know that there will only be one input that maps to a unique output. We can't have more than one input that is the same. Let's demonstrate that looking at an example. If we look at this set, so we have our curly brackets, we know there's a set, and inside we've got a number of brackets separated by commas. So this shows us that we have 3 couples, and each of these 3 represents an input with its own unique output. 1 is the input, and 3 is the number 1's output. Now, if you can look at each of these couples, it becomes quite obvious what the rule of this particular function would be. It seems that you have to add 2. So the input plus 2 gives us our output. Now, as we do not have any more than one of the same input, then this looks like it is suitably meeting our requirements. It is a function. So we might have to decide if a function exists based on looking at its mapping diagram or looking at the set of couples. If we look at this set of couples, we notice that the number 1 appears twice. We cannot have more than one of the same input, and therefore this set does not represent a function, as the input 1 appears twice. We know as well that every input can only have one output, and this shows the number 1 changing to 3, but also the number 1 changing to 2. So there's 2 reasons why this does not represent a function. Another way to represent our functions is the use of a table. And this special table is called an input-output table. We might even be asked to create one in an exam question. An input-output table can be used to show functions, just like a mapping diagram. We can use our couples to help us create our input-output table. Our input-output tables look like this. There are 3 columns. The first is for the inputs, and we will list each of our inputs underneath the heading Input. The next column is for the rule, where we perform the calculation of the function itself. For example, in this function, the rule is to double and add 4. So you can see that in this column, we have the workings for each of our inputs. We start off with that input, we multiply it by 2, hence the doubling, and we add 4. So in this middle column, it's very important that we write as much of our calculations and show our workings as thoroughly as possible. And then the third and final column is for our outputs, the answers once our input has gone through the function. So 1 doubled is 2, add 4 makes 6. You can see from our couples that the first numbers, the inputs, appear in the first column, and the second numbers, our outputs, all appear in the third column, and they must be beside the correct input. So 1 is level with its own output 6, 3 and 10, and 4 and 12. It's very important that you show full workings in this middle column, and remember your BIMDAS. Let's have a look at an example question. From the following ordered pairs, and we can see that this time we have a set, we've got T, and in this set we've got a number of couples. We've got -5, 1, 2, 6, and +5 as the beginning elements. They're all different, so that suggests at the moment that it would be sufficient to say it's a function. Draw a mapping diagram to illustrate the relation T. So we have all of our inputs put into one oval, and we make sure that we have our little dots. Our oval is drawn as neatly as possible. It's okay if you prefer to use a compass and make it a circle. We know that we write the writing then in pen. We then draw our output oval and circle beside it. Try to get it as similar or as close to the same size as the input oval or circle. And we must make sure then that we connect our correct inputs to our outputs. We then also make sure that we label, so in this case we know that it is called T, above our mapped arrows. Part B asks us, is the relation T a function, and explain your answer. So let's check some of the important pieces of information. Does every input have an output? Well, as you can see, there is an arrow from every input to an output, so it meets that first requirement. Does every input have a unique output? Now you can notice that 1 maps to 1, 2 to 4, 6 to 36, they look okay. Interestingly, we can see that both -5 and +5 have the output 25. So this is an example of many, more than one, going to 1. Now, can you remember, is that sufficient for a function? Well, yes. Yes, it is. Remember when we talked about -2 and +2 having an answer of 4 in a function that was squaring? Well, this is exactly that. Both -5 and +5, when multiplied by themselves, give the answer 25. So this is many to 1, and many to 1 is okay for a function. So therefore our answer is T is a function. Each and every input has only one output.